NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will build an intuitive step-by-step algorithm to analyze quadratic equations of the form ax squared plus bx plus c equals 0 when two real roots exist and x2 is greater than x1. We will use signs of c over a, the sum of roots negative b over a, and the discriminant delta to decide where the roots lie on the number line and whether they exist or repeat. Two key facts guide us. By Vieta's formulas, the sum of the roots equals negative b over a, and the product equals c over a. The discriminant, delta equals b squared minus 4ac, tells us whether the roots are distinct, repeated, or non-real. Case 1. If c over a is less than 0, the product of the roots is negative, so the roots must have opposite signs. That means x1 is negative and x2 is positive. Now, compare the sum negative b over a. If the sum is positive, the positive root must dominate in magnitude. The absolute value of x2 is greater than the absolute value of x1. If the sum equals 0, then b equals 0, and the equation is symmetric x equals plus or minus the square root of negative c over a. If the sum is negative, the negative root dominates. The absolute value of x1 is greater than the absolute value of x2. Case 2. If c over a equals 0, then c equals 0. The equation factors as x times ax plus b equals 0. So one root is 0, and the other equals negative b over a. Important note on special relationships. If c over a equals 1, then the product x1 times x2 equals 1, meaning the roots are reciprocals of each other. If c over a equals negative 1, then x1 times x2 equals negative 1, so the roots are opposite reciprocals. Case 3. If c over a is greater than 0, then the product of the roots is positive, so the two real roots, if they exist, must have the same sign. To decide further, we examine the discriminant delta and the sum negative b over a. If delta is greater than 0, there are two distinct real roots. If the sum negative b over a is positive, both roots are positive. If the sum is negative, both roots are negative. If delta equals 0, there is a repeated real root. If the sum negative b over a is positive, that repeated root is positive. If it is negative, that repeated root is negative. If delta is less than 0, there are no real roots. Let us connect these rules with a quick parabola intuition. When c over a is less than 0, the y-intercept and the leading coefficient have opposite signs, forcing the graph to cross the x-axis on both sides of 0. When c over a equals 0, the constant term vanishes, so x equals 0 is a root. When c over a is greater than 0 and delta is positive, both intersections lie on the same side of 0, decided by the sign of negative b over a. Now, let us test the algorithm on two quick examples. Example x squared minus 5x plus 6 equals 0. Here, c over a is positive, and delta is 25 minus 24 equals 1, which is positive. The sum negative b over a equals 5, positive, so both roots are positive. Indeed, 2 and 3. Next, x squared plus x minus 6 equals 0. The product c over a is negative, so roots have opposite signs. The sum is negative 1, negative, so the negative root has larger magnitude. Indeed, the roots are 2 and negative 3. In this example, we will analyze how many real roots the given equation has for all real values of m using the discriminant. We will follow a clean, step-by-step process. Step 1. Write down the original equation. We will transform it into standard quadratic form in x. Step 2. Expand the square and move all terms to the left side. The expansion of 1 minus 2x squared is 1 minus 4x plus 4x squared. Step 3. Combine like terms to get standard form. Negative 4x minus 2x is negative 6x. So the equation becomes 4x squared minus 6x plus 1 minus m squared equals 0. Step 4. Use the discriminant. The discriminant delta equals b squared minus 4ac. This will tell us how many real roots we have. Step 5. Substitute the values of a, b, and c with a equal 4, b equal negative 6, equal 4, b equal negative 6, and c equal 1 minus m squared. Delta equals negative 6 squared minus 4 times 1 minus m squared. Step 6. Simplify the numbers. Negative 6 squared is 36, and 4 times 4 is 16. Therefore, delta equals 36 minus 16 times 1 minus m squared. Step 7. Distribute the negative 16. That gives 36 minus 16 plus 16m squared. Step 8. Combine constants. 36 minus 16 is 20, so delta equals 16m squared plus 20. Step 9. Visualize delta as a function of m to see why it is always positive. We plot delta of m equals 16m squared plus 20. This is a parabola opening upward with its minimum at m equals 0. At m equals 0, delta equals 20, which is strictly positive. Therefore, delta is greater than 0 for all real m. Step 10. Conclude the number of roots. Since delta is positive for every real m, the quadratic in x always has 2 distinct real roots. Final answer. For all real m, there are 2 distinct real roots. Recap. We expanded to standard form, identified the coefficients, used the discriminant, simplified to 16m squared plus 20, and observed it is always positive. Therefore, 2 roots for every real m. In this lesson, we'll solve a classic parameter problem for quadratics. We want all values of m such that the quadratic has 2 roots with opposite signs. Let's begin with the example and state the equation clearly. Quick challenge. What is the condition that guarantees 2 roots of opposite signs? The key idea is the product of the roots. Let's write that down formally and apply it. For our equation, equals 3 and c equals m squared minus 4. Substitute those into c over a less than 0. Multiply both sides by 3, a positive number, so the inequality direction does not change. That gives m squared minus 4 is less than 0. Now add 4 to both sides to isolate m squared. We get m squared less than 4. Take square roots. Because we are dealing with a square, we switch to an absolute value statement. So the absolute value of m is less than 2. Finally, convert the absolute value inequality into a compound inequality. That yields negative 2, less than m, less than 2. To build intuition, here is the solution on a number line. We shade the interval from negative 2 to 2, open at the endpoints. Summary. We use the product of roots condition c over less than 0 to guarantee opposite signs. Substituting at equals 3 and c equals m squared minus 4 reduced the inequality to m squared less than 4, which simplified to absolute value of m less than 2, or the final answer negative 2, less than m less than 2. Great work! In this guided example, we will solve for the parameter m so that the given rational equation in x has a double root. We'll proceed step by step and keep the narration perfectly synced to each line that appears. First, let's display the problem clearly. Step 1. Write the original equation as our starting point. Step 2. Eliminate the fractions by cross-multiplication. The rule is a over b equals c over d implies ad equals bc. Multiply both sides by m times x minus 1 times m minus 1. Step 3. Expand the inner terms. We use the distributive property. A times b plus or minus c equals ab plus or minus ac. Note that x times x minus 1 equals x squared minus x. Step 4. Distribute the remaining factors to fully expand both sides. We expand products term by term. On the left, multiply by m. On the right, multiply by m minus 1. Step 5. Move all terms to one side to set the equation equal to 0. If a equals b, then a minus b equals 0. Subtract the right-hand side from both sides. Step 6. Combine like terms and simplify. A minus a equals 0, so cancel identical terms. The mx squared terms cancel, as do the mx terms. Step 7. Arrange in standard quadratic form in x. X squared plus bx plus c equals 0. Treat the m terms as a constant and rewrite the equation. Step 8. For a double root, the discriminant must equal 0. Delta equals b squared minus 4 ac equals 0. We'll now apply this condition. Step 9. Substitute a equals 1, b equals negative 1, and c equals negative m times m minus 1 into the discriminant. Equals negative m times m minus 1 into the discriminant. This is direct substitution. Compute b squared minus 4ac with these values. Step 10. Simplify the discriminant equation. Negative 1 squared is 1, and minus 4 times a negative becomes plus 4. This yields 1 plus 4, m times m minus 1 equals 0. Step 11. Recognize a perfect square. Rearranging gives 4m squared minus 4m plus 1 equals 0, which is 2m minus 1 quantity squared. So we have 2m minus 1 squared equals 0. Step 12. Apply the square root principle to solve for m. If a squared equals 0, then a equals 0. Setting 2m minus 1 equal to 0 gives m equals 1/2. Our final answer is m equals 1/2. In this video, we will solve for m so that the quadratic form from the equation open parenthesis x squared minus bx close parenthesis over open parenthesis ax minus c close parenthesis equals open parenthesis m minus 1 close parenthesis over open parenthesis m plus 1 close parenthesis has two opposite roots. Two opposite roots means the solutions are r and negative r, so their sum is 0. First, let us write the given equation clearly. Before we do the algebra, here is the key geometric idea. If a quadratic has opposite roots, its graph is symmetric about the y-axis. That symmetry happens when the linear coefficient is 0. Let us visualize this. The green parabola has roots at -2 and +2. Notice those are opposite numbers, and the graph is perfectly symmetric about the y-axis. In algebraic terms, that symmetry corresponds to the linear coefficient being 0. That is the condition we will enforce after we convert our given equation into standard quadratic form. Step 1. Clear denominators by cross multiplication. Multiply both sides by open parenthesis, ax minus c close parenthesis times open parenthesis m plus 1 close parenthesis. Step 2. Expand both sides using the distributive property. Step 3. Bring every term to the left-hand side to make 0 on the right. Step 4. Group like powers of x into the standard quadratic form, ax squared plus bx plus c equals 0. Ax squared plus bx plus c equals 0. Step 5. Factor the linear coefficient b for clarity. Now, the key step. For opposite roots, the sum of roots is 0, which means the linear coefficient b must be 0. Set the bracketed factor equal to 0 and solve for m. We must also note conditions. M cannot be -1. Otherwise, the original right-hand side is undefined, and a plus b cannot be 0 for the solution formula. Under these conditions, m equals the fraction a minus b over. Example, we will find all real values of a such that the quadratic x squared minus 2ax plus a plus 6 equals 0 has two negative roots. To guarantee two negative roots, we use Vieta's relations. For a quadratic, ax squared plus bx plus c equals 0. The sum of roots is negative b over a, and the product of roots is c over a. We need three things at once. 1. Product positive, so they have the same sign. 2. Discriminate positive for two distinct real roots. 3. The sum is negative, forcing both roots to be negative. Step 1. Product positive. Here, a equals 1, and c equals a plus 6, so c over a is a plus 6. We require a plus 6 greater than 0, which gives a greater than -6. Step 2. Discriminate positive. The discriminant is b squared minus 4ac. That is -2 a quantity squared minus 4 times 1 times a plus 6, which simplifies to 4 1 times a plus 6, which simplifies to 4 times a squared minus a minus 6. Requiring it greater than 0 is the same as a squared minus a minus 6 greater than 0. The roots of a squared minus a minus 6 are -2 and 3, so the inequality holds when it is less than -2 or greater than 3. Step 3. Sum negative. The sum of roots is negative b over a, which here is negative of -2 over 1, or 2a. We want that less than 0, so a is less than 0. Finally, we intersect the three conditions. The intersection of a greater than -6, the union of a less than -2 or a greater than 3, and a less than 0 is the interval from -6 to -2, open at both ends. Therefore, the set of all. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.